Good afternoon. Our topic in this video is multiple comparisons in analysis of variance. We're going to be looking at multiple comparisons in one-way analysis of variance, but there are times when you also need to make multiple comparisons in other forms of analysis of variance, and most of these techniques are applicable. And this is covered in chapter 12 of your textbook. So multiple comparison techniques are used when you need to perform multiple t-tests. In other words, multiple comparisons are t-tests or t-tests like tests in that they are pairwise, contrast between two means. And the null hypothesis is the contrast between two means, or the difference between two means, significantly different from zero? So why perform a specifically multiple comparison technique instead of a t-test, since they answer the same question, is because of type 1 error. So if you set your alpha at 0.05, that means that you have a 5% chance of making a type 1 error, or claiming that the contrast between two means is non-zero, when in fact it is just within the realms of chance less than 0.5%, less than 5%. So that's what you do when you're making just one comparison. But if you're making a group of comparisons, your type 1 error rate will be what we call inflated, and multiple comparison techniques reduce that type of inflation. So the issue with this type 1 error inflation is that if you have a number of hypotheses tests, particularly all using the same set of variables, your probability of type 1 error increases. And it isn't what you have set as the alpha, it's actually an inflated alpha. So the proper unit is what we call a family of contrasts. Some people extend this even further, but we usually use what's called family-wise error rate for the type 1 error rate with a group of multiple comparisons that involve the same set of variables. And the formula for the level of type 1 error inflation is that with a group of contrasts, your actual family-wise error is 1 minus your error rate per contrast. Let's say that's your alpha, and let's say that you've set your alpha at 0.05 to the power of the number of available contrasts. Oh wait, the number of independent tests that you choose to make. So if you choose to make 6 pairwise tests with following an rejection of the omnibus null hypothesis in ANOVA, so your K there, the number of pairwise tests you want to make, is 6. Even if you kind of mentally set an individual an individual means comparison at 0.05, your actual type 1 error rate for your group of tests is 0.265, which people would consider outrageous. In other words, you have a 26% chance of finding an effect when in fact the effect, the non-effect, the finding of the difference between two means is likely due to chance. So we take measures to control type 1 error inflation. And they're basically 3 particularly classic methods for doing this. We call these post hoc tests because these are unplanned tests. These are tests that you perform only after rejecting the omnibus null hypothesis. As you saw in a prior class, if you reject the null hypothesis for the null hypothesis, there is some difference between two means, at least two means, when you have more than two levels of the independent variable. You don't actually know where the difference between the means is. If you have three levels of the independent variable, the difference could be between mean 1 and mean 2, between mean 2 and mean 3, or between mean 1 and mean 3. Or it could be more than one of those, but you don't know because you haven't done pairwise comparisons. And so then you go on to these post hoc tests. They're always non-directional because they're not planned. And the three most classic ones are Bonferroni, Tukey, HSD, and Chaffee. And they all have their uses. Bonferroni, you may have heard of before. I'm not going to discuss that. And I will go into some detail on Tukey, HSD, and Chaffee. The Bonferroni simply adjust the alpha rate that you set, 0.05, by the number of tests. So it's pretty straightforward. It's extremely straightforward. I believe that your textbook also refers to it as done. I hope I haven't added confusion because it's something other than done. But if you only have three tests, because you only have three levels of the independent variable, so you're comparing 1 to 2, 2 to 3, and 1 to 3, then you divide an alpha, say, of 0.05 by 3. And that's the level of significance that you are trying to reach. So it's quite simple, but with more groups than 3, you rapidly whittle away your alpha rate until it's quite a barrier to overcome, in which case other tests can be more powerful. In other words, they can control your alpha rate over more comparisons. Tukey only covers simple pairwise contrasts, which is often just what you want to do. You have no theory to start with, so really why dig very deep? But the Chaffee test covers all possible pairwise contrasts and combinations of that yield pairwise contrast. So say that you have, and I'm going to stick with three total levels in an independent variable, and 2 of them are treatment conditions, and 1 of them is a control group. It's possible you would want to compare the average of the 2 treatment groups to the control group. In other words, what you're interested in there is whether any treatment is better than none. So in that case, you would need to use the Chaffee test because it can cover things that end up being pairwise, and that the average of 2 compared to a third, but require a manipulation of the means in the independent variable before it can be tested. So you use the Chaffee test in that case. And we're going to look at both of those. So for Tukey's, back to a segment of the general linear model that I've presented before. See if I can bring up an annotation here. You start, you've got, as before, we're still working with a continuous variable, a single continuous variable, and a single, in case of one-way ANOVA, variable as an independent variable, and its constraint is that it is not a continuous or interval level scale. It's a set of groups. And if it is ordinal, you probably want to go into a trend because it's ranked. So we're not going to cover that now. We'll cover it in class. But if it's not ordinal, then you're going to move into the world of post hoc tests. You don't quite go into the world of post hoc tests because you may have some a priori hypotheses. In other words, you may have set a group of hypotheses before you even started, in which case you can just go straight to tests of those. You don't even, in fact, need to go down this corridor. You don't even need to reject the omnibus null hypothesis, because even though you tested more than two groups, you are only interested in a subset of those contrasts. That's a priori hypothesis. From the start, you are only interested in a limited subset, and then there are techniques to test those. But let's say you had no a priori hypotheses. Well, then in ANOVA, you have to reject the null before you can move on. And if you don't reject the null, you just stop. If you have no a priori hypotheses, you don't need to reject the null. But if you have no a priori hypotheses and you fail to reject the null hypothesis, that's a stop. But if you do reject the null hypothesis, then the question is, where is the difference among the means? Because in ANOVA, you have more than two. So let's say you reject the null. If you are only interested in the comparisons between the means of the groups that you have set up, you're not interested in the comparison between, say, the average of group 1 and 2 and the and group 3. So you're only doing simple pairwise comparisons, and you have equal variances. That means you've retained the assumption of homogeneity of variances. That does not necessarily require equal sample sizes, because there's a very minor variation in Tukey that doesn't require equal sample sizes. But let's say that you have both equal variances for pairwise comparisons after you've rejected the null hypothesis in a one-way ANOVA, and you do have equal cell sizes. Then you do this classic test called the Tukey HSD, where HSD stands for honestly significant differences. And that's what we're going to look at right now. So, wait, I have to get rid of my annotations. Sorry about that. I think I should have pressed clear, but it's fine. So when do you use Tukey? I've basically already covered this. You'll use it if there are more than two levels or groups in your independent variable. When you have a, the independent variable is statistically significant, or you've rejected the omnibus null hypothesis, the F test. When you're only interested in pairwise comparisons between means, when the homogeneity of variance assumption is upheld, which you'll see in the ANOVA results on SPSS as Levine's test of homogeneity of variances. And you have equal cell sizes, that's the HSD test. If you have unequal cell sizes, you're going to find a Tukey-Kramer test, which I'm not going to go through in this presentation, but it's a variation in Tukey for any unequal cell sizes. And remember that equal cell sizes is ideal because you're much more likely to accept the assumption of homogeneity of variances. And then, so how do you actually perform the Tukey HSD test? Well, what it is it's an adjustment to your critical statistic. And you generally do not calculate the critical statistic in a Tukey test. Instead, what you calculate is the minimum difference between any two means that qualifies as statistically significant at a given family-wise alpha. So it ends up being just a numerical comparison between two means. like the denominator, or I'm sorry, the numerator in a t-test. But to get this critical statistic, you have to do some manipulations. And interestingly, at least in my version of SPSS, which may be a little prior, is a little prior to I use version 25 usually. 27 has some additional features. It may report the actual HSD. In version 25, the HSD is not reported. You just see which pairwise mean comparisons are statistically significant. So, like the T family of statistics, there's a distribution, like the T distribution, family of distributions. There's a family of distributions particularly for this kind of test, and it's called Q. And you have a Q table probably in your textbook. But so you look up the critical Q, and the critical Q is a function, as you can see in this formula, of your alpha level. So for instance, if your alpha level family-wise is 0.05, this value is 0.95, and your degrees of freedom in your error term, and that is for the omnibus null hypothesis. So you're going to see that in SPSS output as the degrees of freedom for the error term, for the mean square within. And it is the total sample size minus the number of groups, and then the number of groups. So you look for the Q statistic at, say, alpha of 0.05 or P of 0.95, depending on how the table is arranged, at the correspondence of the degrees of freedom for the error term. That's the mean squares within degrees of freedom, or the sum of squares within degrees of freedom, and the number of groups. And then you use that critical statistic to calculate the term which is on the same scale as your means. It's one of the things that's nice about it. It just looks like a value on the scale of your means. So if your means are inches, it's a value in inches. And you get that by multiplying this critical statistic times the standard error of the contrast. Now, the standard error of the contrast is the square root of your mean square within times, or divided by the within group n. And this is the mean square within from the ANOVA. So that's kind of from the the F test, the overall ANOVA. So you've already got that. If you've rejected the null hypothesis, even if you haven't rejected the null hypothesis, you're kind of not in the world of Tukey unless you have this term already. You have found this term in your tables. You know your group size. Again, you need the Tukey-Kramer, which we're not going to cover, if you have unequal group sizes, right? Because this is one term, it's expected to remain constant for any pairwise comparison. So you can't use the HSD. But basically, the concept is the same. So we're just going to do regular, simple Tukey HSD. And you compare your means. So say group 1 has a mean of 20 and group 2 has a mean of 25. Your what you're comparing is whatever the value is of your HSD to 5. And if the value of the HSD is 4 and your pairwise comparison is 5, then you have rejected the null hypothesis, and that difference between means is statistically significant at the alpha 0.05 level, the family-wise. So these Q values are found in table 8.9, and remember this is, I'm sorry, I believe it's the 3rd edition of the textbook. It may have changed in the new edition. And I'll let you answer that question for yourself, and we can look it up if you have any questions in class. Oh. Okay. Okay. So once you have found, this is kind of, again, something I already said, but it spells it out a little bit more detail. You have calculated the HSD. You found your critical statistic in the tables, and you have calculated the standard error of the difference between means by taking your mean square within from the overall test, dividing it by your group size, and taking the square root of that term. And now what do? Well, you take the difference between the means of each of conditions you're comparing. And it's easiest if you start with the largest difference. This isn't actually necessary. It's just kind of traditional, but it's not particularly necessary. So you start with the largest difference between any two means. Find out, is it statistically significant? The convenience of this is if the largest pairwise difference is not statistically significant, none of the rest of them will be, because they're all smaller. If the biggest one isn't larger than the HSD, then none of the smaller ones will be larger than the HSD. I mean, hopefully you've got at least one. You would think, having rejected the omnibus null hypothesis, that you would have at least one, but actually you can reject the null hypothesis and not have any pairwise differences that are statistically significant. You know, we hope that doesn't happen. So you start with the larger difference. If the difference between the means is at least as large as the HSD, you can reject the null hypothesis. And then you can repeat, so then you can go to the next largest difference and so on. And then once you get to a difference that isn't significant, none of the smaller differences will be significant. Again, this business of ranking them is optional, but if you don't rank them, you have to go through every single one. There is a similar test called the Newman coils that is a little bit more powerful. And that's because the Q statistic, actually the critical Q, changes for each test. So, okay, I hate to go into this much detail, but in the regular Tukey, you have set a single critical Q statistic for the overall family of tests. So say you have 3 tests. Compare group 1 minus 2, group 1 minus 3, and group 2 minus 3. So you've set the critical statistic, and one of your terms there is J, which is your 3 groups. Okay, so say that you reject the null hypothesis using Tukey for the first test. Well, you have 2 other tests, but you have set your J in calculating this critical Q at 3. Newman coils allows you to adjust now that Q statistic for the fact that you only have 2 tests left. It's not something you want to do by hand. It may be even slightly more detailed than that, but it is available in SPSS if you want to ask for it. It often doesn't make a lot of difference. Okay, so that's Tukey. We will perform at least one Tukey in class. But those are the outlines so that you can be prepared before you come in, both through your book and through this video. We're now going to do Scheffé tests, which are for when you, the similar case, you have started with a dependent variable that's continuous and your ordinal or categorical independent variables. You're actually, see if I can get my annotations up again. We're actually not going to go down this road because in this particular case, we're not going to take the ordinal. So we're only looking at ordinal is no. And so you're not ordinal, you're just categorical. You have no a priori hypotheses. So you're no to both of these. You have not failed to reject the null, so you don't have to stop. So you're going on. You have categorical dependent or independent variables and you've rejected the null. So we continue along this line. But you say pairwise comparisons? No, I want to compare multiple groups to one other. Like an average, often it's an average of 2 or 3 or 4 groups to one, or the average of 2 groups to the average of 2 other groups. And you can't do that with Tukey tests. You have to do that. If that is no, you have to go to Scheffé. And to my knowledge, Scheffé is really the only one that you can go to. So how do you do a Scheffé? You're doing it when you have rejected the null hypothesis. Perhaps you don't find it using simple pairwise. You don't find the mean difference using simple pairwise comparisons. So you want to hunt around with Scheffé. The problem with Scheffé is that, you know, the average difference between 2 levels, 2 pairwise, 2 means compared to the average of another 2 pair means is often, well, what is this? It becomes quite a lot like fishing at a certain point with Scheffé. And the whole world of post hoc tests is a little bit fishing, but Scheffé is particularly fishing. Actually, people don't perform Scheffé very much. If they're going to have some kind of complicated comparison, like the difference between the average of 2 means and the average of another 2 means, it's usually going to be a priori, because it's going to be theoretically hard to excuse that as post hoc. You're probably going to have a theoretical reason that would be a hypothesis even before you ran the ANOVA. So it's an a priori hypothesis. But Scheffé is basically always taught because it is the test that you can use under all post hoc circumstances.